Now we introduce something related to normal subgroups. Here's a lemma. And let H be a subgroup of G. And we define a new subset of G by this and G of H. So this H defined by all elements of G such that x inverse times H times x is equal to H. Then this is a subgroup of G containing the subgroup H. So let's prove this. And from this definition, and we're assuming H is a subgroup already, so it is clear that all elements of H are included in this subset. Okay? So by definition, H is a subset of G of H. And then let x and y be elements of this subset. Then that means we have x inverse H, x is equal to H, and y inverse H, y equal to H. Then we want to check the subgroup criteria. So first, xy inverse H, xy. So this is y inverse x inverse H, xy. So this is equal to H, but this is equal to H. So therefore, xy is an element of this subset. And also, H is equal to this, obviously. This is the identity element of the group G. And therefore, and E is x times x inverse H and x times x inverse, and that is x inverse inverse. So, and this one is equal to H. So we have H x. So this one is equal to H. So this means x inverse, if, of course, we are assuming this, if x is an element of Ng of H, then x inverse is also an element of Ng of H. Therefore, by the subgroup criteria, Ng of H is a subgroup of G. And we are done. So according to this lemma, this subset is a subgroup. So we give it a name. So given a subgroup H, here's a definition. We define Ng of H as in the lemma and this is called the normalizer. Normalizer of H in G. So what does this mean? We have learned a normal subgroup is a group such that let's say H is normal if and only if for all elements in G, x inverse h, x is equal to h, right? But not all subgroups are normal. Okay, so even if h is not normal, suppose h is not normal. Normal. But then if we consider the normalizer of h, then if just focusing on the elements of this subgroup, then h behaves as if it is normal. But it is normal not respect to the entire group G, but it is normal as long as we only look at the elements in this normalizer of H. So that's what normalizer is. This is very similar to the relationship between the central element and elements and the centralizer of that element. Okay, and as we have seen before, an element of G is called central if for all elements in G we have x inverse A, x is equal to A. But of course, not all elements are central. But if we consider the centralizer of A, which was denoted by Cg of A, and defined as, what was the definition here? As all elements of G such that x inverse A, x is equal to A. Then this is called the centralizer of A in G, right? So as long as we consider the elements in the centralizer, then this element A can be considered as a central element. Just like that. So even if H is a subgroup H is not okay. If H is a subgroup which is normal, then that means for all elements in G we have x inverse H, x is equal to H. But we consider the normalizer of H. So even if this is not H is not a normal subgroup, as long as we consider the elements in this normalizer, we may consider this any subgroup as a kind of normal subgroup. Normalizer of H. So the central elements and centralizer were concerned with each element, but normal subgroups and normalizer of subgroups are concerned with a subgroup. And we can see something parallel here. Another way to put it is that the normalizer of a subgroup H is the largest subgroup of G. The largest subgroup of G in which H is normal. And if the normalizer of H is equal to G itself, then that means H is a normal subgroup in G. So this means H is the normal subgroup in its original sense. Now we can present the next theorem. And let H and N be subgroups of G, and also N is normal. So these are the assumptions. Normal in G. Then we have Hn equals to Nh. So in a sense, they commute. And Hn is a subgroup of G. Okay, let's prove this theorem. Okay, first let's try to show that Hn is equal to Nh. Okay, first of all, Hn is a subset defined by this. So its elements are all expressed as a product H times N, where H is an element of the subgroup H, and N is an element of the normal subgroup N. Okay. Then, since N is a normal subgroup, then that means we have H inverse. Maybe I should write H here. H and H inverse belongs to N due to the definition of the normal subgroup. And of course, we assume H is an element of H and N is an element of N. Okay, for each such element of H and element of N, we have this relation. Now, let's see. Hn is H and H inverse H. So we multiply by H inverse and H like this. Then this part belongs to N. And this H is an element of H, so this belongs to N times H. So each element of Hn is also an element of Nh. So therefore, Hn is a subset of Nh. Okay, and we can also show in a similar manner. So just swap the roles of H and we can also show the opposite inclusion. So Nh is a subset of Hn. Let's say just similarly. So therefore, Hn is equal to Nh. Okay. Now let's show that Hn is a subgroup. So let's show this subgroup of H. Okay. Suppose let's just write let A, B be elements of Hn. Then there exists some elements H1, H2 in H and N1, N2 in N such that A is equal to H1 and 1 and B is equal to H2 and 2. Okay. Then we want to show, of course, we want to apply the subgroup criteria. So let's check that. AB is equal to H1, N1, H2, N2. And let's see. So we want to show that this is an element of Hn. Okay, so H1, let's see, it may, okay, let's try H2 here, H2 inverse, so we apply this one, H1 and N1 is here, and H2, N2. Okay, and by associativity, H1, H2, so let's group these factors together. H2 inverse, N1, H2, N2. Okay, so H1 and H2 are elements of H, so H1 times H2, so they are subgroup. This is H is a subgroup, so this is an element of H, and H2 inverse N1 H2, this is, since N is a normal subgroup, H2 inverse N1 H2 is an element of N. Okay, and of course N2 is an element of N by assumption. So therefore this times this, H2 inverse N1 H2 times N2 is an element of N. So therefore this part is an element of H, and this part is an element of N. Therefore this entire thing is an element of Hn. So therefore this product is an element of Hn. And also A inverse is H1 N1 inverse, which is N1 inverse H1 inverse. And since N and H are both subgroups, so N1 inverse belongs to N and H1 inverse belongs to H. So this is an element of NH, but this is equal to Hn. Therefore, every inverse is an element of Hn. Therefore, Hn is a subgroup of G. And we are done. Okay, let's see an example. This is our favorite example of the dihedral group of order 8 called D4. And we know that this has a subgroup, several subgroups, but here we consider this subgroup and try to find the normalizer of this one. So what is it? And we know that a normalizer is a subgroup, so it should contain the identity element. Yeah, but what are other elements? To see that, we see the commutativity of all the elements with D. Okay, so let's see. A inverse D A inverse is C, and CD is H, and HA is G. So this is not equal to D. Therefore, A is not an element of this normalizer, and B inverse D B. B inverse is B, and BD is G, and GB is D. So this is okay. So B should be an element, and C inverse D C. C inverse is A, and AD is F. And FC is G, which is not equal to D. So we reject this element. D inverse D is of course D, so D should be here. And F inverse F inverse is F, and FD is A, AF is G, which is not equal to D, so we reject this element. G inverse DG, G inverse is G, and GD is B, and BG is D, so G should be an element. And what about H? At this point, actually we already know this should be it, but anyway, let's try this. H inverse is H, HD is C, and CH is G, which is not equal to D. So this should be the normalizer of this subset, a subgroup ED. And similarly, we can find the normalizers for other subgroups of D4. For example, EG is a subgroup, and its normalizer should be E, B, D, G. And the normalizer of EF is E, B, F, H. And you should check that. Next, let's approach the same problem with a different method. So again, we want to find the normalizer of this subgroup E and D. Okay, we already know the answer, but suppose we just don't know. And recall that the center of this group D4 is E and B, and the center is a subgroup of D4 here, such that they commute with all elements of this group D4. So this means this center of the group should be a subgroup of the normalizer of any subgroup, because the normalizer is supposed to be the subset of the group, such that each element of this normalizer should commute with the elements of this subgroup. Okay, so this is a superset of ZD4. Okay, so this should include E and B at least. Okay, and also this should be a superset of ED, of course, and times and EB. So that is, so E, B, D, and D times D times B is G. So this is equal to this subset, and we know that this is a subgroup already, because we enumerated all the subgroups of this D4. And we already know that this normalizer cannot be equal to D4 itself, because ED is not a normal subgroup. If it is a normal subgroup, then this should be equal, but it's not, so they are different. But there are no other subgroups whose size is between this and 4 and 8. So the subgroup we have got here should be the maximum or maximum subgroup such that it commutes with all elements of this subgroup E and D. Therefore, the centralizer of ED is this E, B, D, and G. Next, consider this example. The set of matrices that are non-singular. So suppose we have a matrix like A, B, C, D. This is non-singular if and only if A, so that is the determinant is non-zero. That is AD minus BC is not equal to 0. Okay. Such set of matrices is called the general linear group. Okay, so which we write, and also we consider the matrices of over real numbers. Okay, so general linear group. So which we write GL. So in this case, we consider 2 by 2 matrices. So this is 2 and over real numbers. Okay. So A, B, C, D such that A, B, C, D are real numbers and A, D, B, C is non-zero. Okay, so this set is called the general linear group of 2 by 2 matrices over real numbers. And this forms a group by matrix multiplication, which you should check. Now, let's find the center of this group. Okay, so that is Z, GL to R. So what is this? This is the set of matrices that are elements of GL to R. Let's say X, Y, Z, T. And the determinant is non-zero. Such that A, B, C, D times X, Y, Z, T is equal to X, Y, Z, T times A, B, C, D for all A, B, C, D in GL to R. Okay, that means the determinant AD minus BC is non-zero. So how do we find this? Suppose X, X, Y, Z, T, this matrix is an element of the center of GL to R. Then we should have this relation for some specific elements of GL to R. For example, let's pick special matrix 1, 1, 0, 1, which is an element of GL to R because the determinant is non-zero. So let's apply this relation to this matrix. So we have 1, 1, 0, 1, X, Y, Z, T, and X, Y, Z, T, 1, 1, 0, 1. So suppose this holds. Then what kind of relationship do we have for X, Y, Z, T? So the left-hand side is X plus Z and Y plus T and 0 and Z and 0, and t. The right hand side is x and x plus y and z and z plus t. So we have x plus z. Comparing the elements, we have y plus t is x plus y, z is z, so this is trivial, and t is t z plus t. So this can be ignored, and from this we have z equal to 0, and from this also, and from this, let's see, y, so x is equal to t. So if x, y, z, t is an element of the center, then we must have, that should be x, y, 0, and x. It should be of this form. Okay. Then let's apply this to, again, this to another special matrix. Let's say 1, 0, 1, 1. So this is an element of GL to R. So suppose this matrix and this matrix commute. So 1, 0, 1, 1, x, y, 0, x, x, y, 0, x, and 1, 1, 0, 1. So the left hand side is x and y and x, y plus x, and x plus y, y, and x, 0, x. So we should have this. Then comparing the elements, and y equal to y, and x equal to x, and y plus x equal to x. So these are meaningless, I mean informationless, and from this and this, from both we have y equal to 0. So after all, we should have x 0 0 x, and of course the determinant must be non-zero, so x squared is non-zero. That means x is non-zero. So the center of this GL2R should have this form, x 0 0 x. So it's a diagonal matrix with the same diagonal element, which is non-zero. So this means the matrices of this form can commute with any non-singular matrices. Next, let's define this subset of GL to R. Is 1, a, 0, 1, where a is any real number. Okay. And let's show that this is a subgroup of GL to R. And indeed, this is an Abelian subgroup. That means this is a commutative subgroup of GL to R. So let's to see this, a 1a 0 1 times 1 B 0 1 and 1, so this is 1 0 0 0 and B, so A plus B and 0 1, so this indeed belongs to H. And we can swap the order and we still get the same result, so it is commutative. And also the inverse matrix of this, you can show that this is 1 0 negative A 1. So just replace this B with negative A and you get the identity matrix. So it's easy to see that this is indeed the inverse of this, and this also belongs to H because negative A is also a real number if A is a real number. Therefore, this H is an abelian subgroup of GL. Okay, next let's try to find the normalizer of this abelian subgroup. So normalizer of H, where for abbreviation this G represents GL to R. Okay, so that means we want to find such a set of matrices that this holds. This is an element of H. Okay, so that means there is some element such that this is equal to 1B01 for some B. Okay, so if we multiply x, y, z, t from the left, we have an equivalent expression that is x, y, z, t, 1, b, 0, 1. Okay, so let's expand this. The left hand side is x plus a z and y plus a t and z and t, x and x b plus y z and zb plus t. So by comparing the elements between left and right, we have this and z equal to z, and so from these we have az is 0. From this we have a t is xb, and this is not so informative. And from here we have zb equal to 0. Okay, so this is 0, this is 0, and we have this. And so these equations must hold for any A. So that means then z must be 0. Okay. So let's see. This is 0. So we have, this is 0, and inverse and a01 x y 0 t. So the inverse matrix of this is let's see, 1 over xt and t minus 1 0 x so let's see, t0 t a minus y 0 0 0 x xt yt t 0 0 0 xt. So xt and xt, and so yt will cancel, and t squared a 0 xt. So we have 1 and ta over x 0 1, which belongs to h. And of course x should not be 0. Therefore, after all, we have the normalizer of h is such matrices x, y, 0, t such that this is non-zero. Finally, we redefine the meanings of the centralizer and the normalizer of a subset of a group. Okay, here are the definitions. Let A be a subgroup of G, which is non-empty. Here we do not assume A is a subgroup, but it's just a subset of G, okay? Then the centralizer of A in G is defined as this: all elements of G such that for all elements in A we have x inverse ax is equal to A. Previously, the centralizer was defined for each element, not for a subset, right? But here we define that for each subset. And the normalizer of A in G is defined as ng of A, and this definition looks pretty much the same as before. The only difference is that now we do not assume this A is a subgroup, but it's just a subset. Okay? And you should try to prove that this centralizer and the normalizer of any subset A are subgroups of G. Okay, so this is a theorem you should prove. And you also note that the centralizer of a subset can be expressed as the intersection of all centralizer of elements in the set A. Centralizer of each element in A. Okay, so this is the centralizer we have defined before. So it's defined for each element. Okay, so this means intersections. Okay, so let's say we have A1, A2, and so on. Then what this means is the intersection. Okay, the centralizer of A1 intersection, centralizer of A2 intersection, and so on for all elements of A. Okay, and similarly, the center of the group G is the centralizer of G itself, which can be considered as the intersection of all elements of G and centralizer of A.